Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Okay. Hello, students, senior 6 chemistry. Welcome back. I hope you're fine. So, Alan is my name, still with you in the chemistry lessons. And we are still on Unit 15, which is about radioactivity. So, we looked at its introduction in lesson 1. Now we are heading on lesson 2, which is about natural and artificial radioactivity. Of course, when we talk of artificial, we are mainly meaning the man-made reactivity. Do we actually have those circumstances whereby the man trigger the disintegration of atoms? Yes, we do. And I'm pretty sure you have some examples or you've already heard of nuclear explosions or the nuclear power plants and so on. Most of them are man-made. So that is what we shall be looking at in today's lesson. So the focus, as usual, I always tell you what we are to go through, so as you know the coverage of the lesson. We are to see how the balance of protons and neutrons bring about the radioactivity for both natural and artificial. Then we distinguish the natural from artificial radioactivity, and we look at the cases of artificial radioactivity which involve nuclear fission and nuclear fission. So those are that is what we shall be discussing, and I invite you to take part in the discussion because this is actually an interesting topic, and I'm pretty sure you are not completely blank about it because you normally watch movies and see explosions in movies and so on. So basically, we are now going to bring that knowledge of the movie into the chemistry or into the class setting. So the key aspects you should not miss in this lesson are exactly the balance between protons and neutrons. We shall look at a few examples and you see how exactly that brings about radioactivity. Then we look at the nuclear fission and the fission. Those are the two crucial aspects that you should not miss in this lesson. And again, I want to forward this warning. After we've covered all this, do not transfer this knowledge and create explosives which will kill people. No, that is not the target. Let me say that before, actually. It is involving too much of explosions or too much of reactions that can lead to production of excessive energy, which is detrimental, at the same time useful. So the point is, when we're done studying, do not transfer the knowledge and make explosives purposely for killing people. So you need to take note on that. So the objectives, of course, they come from what we look at, and they involve illustrating how the natural radioactivity occurs, then distinguish between the natural and the artificial radioactivity. Now, let's go to the lesson content. Stability and instability of the nucleus and how it relates to radioactivity. From lesson 1, you notice that heavier isotopes or heavier atoms do disintegrate to form stable, smaller atoms. And in the process of that disintegration, they emit radiation in form of energy and a few more particles, as we looked at the alpha decay, the beta decay, and so on. Now, the question is exactly what brings in the instability of the nucleus? What brings in the instability of the nucleus? A point to note, when we are looking at radioactivity, we are looking at the disintegration of the nucleus in here. Of course, the atom is made up of the nucleus and the orbitals, whereby the electrons are moving in. As you see, this is the orbital, but we're looking at the nucleus. So when we are looking at the instability or stability of the atom, we direct the base on the nucleus. So the reason why radioactivity occurs is because of the balance between the number of neutrons and protons within the nucleus. This is the point of emphasis in here. So if they are not balanced well, then decay inevitably happens to form stable isotopes. This is what happens. And this decay involves losing or loss of energy to create stability. Now, exactly how is the balance between neutrons and protons existing or causing radioactivity? How does it really bring about that? This takes us to the stability conditions. You see from our slide, they are vibrating because they are not stable. So what is the aspect? Red implies proton, and this black implies neutron. They are conditions that bring about radioactivity or that bring about instability. The first condition is if an atom is having proton number greater than 83, it is considered to be heavy. So it is susceptible to radioactivity, or it is susceptible to disintegrating to form a stable component. Let's use our specific example of the periodic table. You remember this? I'm pretty sure you do because we looked at it in the previous lesson. Let's still base on it. I'm going to start on bismuth. This has, as you see from bismuth, moving all along, all these are radioactive. Bismuth has 83. So these are much more stable. So if you have 83, then that atom is bigger, 83 and above, number of protons, then that atom is bigger and it is susceptible to decompose or to decay, forming stable atoms. Something which I need to clarify here is, do not be confused by this. I'm saying from 83, you move, you pass here, you go, and pass here, you go this way. As you see in the highlighter. A student may wonder, how come these are here and yet they are not undergoing decomposition or decay? These which you see here, they belong to this part. They are lanthanoids. They belong they belong right here. So in this case, you're not yet up to 83. Then this part is what you see here, the actinides. From your knowledge of inorganic chemistry or the periodic table, that should directly tell you what I'm meaning. But again, another scenario comes in. How come this element with 43 protons is also radioactive? It is having the proton number less than 83. How come it is also radioactive? That's a question. We are saying the first condition, be heavy, having proton number greater than 83, as you see from bismuth, going downwards. But again, we have this element which is radioactive, and it is having the proton number less than 83. Why? Any idea? That is now the case 2. Case 2. Or other conditions bring about radioactivity. If you're having proton number less than 83, then the balance between the number of protons in the nucleus and the neutrons also brings about instability and so radioactivity. Let's use specific examples in here. The first case, if the proton number is greater than the neutron number, the nucleus is unstable. This is the specific example, carbon. You know our bodies are all occupied, or they are made up of carbon. It's part of the elements. The plants are also having carbon in their makeup, so carbon naturally exists. But we also have the radioactive isotopes of carbon. How do they come about? Like carbon-11, this is how it is written. It's having proton number 6, neutron number 5. The presence of neutron number, which is less than the proton number, makes this atom unstable, and so it is a radioactive isotope. You notice that? Because ideally we expect at least the proton to either be equal to neutrons or the neutron relatively greater than the proton. But if you have neutrons less than the proton, then that isotope is unstable. This is a specific example. Another case is carbon-14, which is always used in carbon dating to determine the age of fossils for dinosaurs, for instance, fossils for all the organisms that died many, many years ago. That is what we call the carbon dating. They use carbon-14. Carbon-14 has 8 neutrons, you see here, and 6 protons. So the condition here is the number of protons are far less compared to the number of neutrons. In other words, the neutrons are far greater in number compared to the number of protons. Also, that brings about instability in the nucleus, making that isotope to be radioactive. Specific example, carbon-14. So you see the isotopes of carbon now. The only 2 stable isotopes of carbon are carbon-13 and carbon-12. Carbon-12, same number of protons and neutrons. Carbon-13, the difference between neutrons, which is 7, and protons is smaller compared to 6 and 8. Of course, it is always in relative to the size of the atom. 6 and 8 brings about instability because carbon is smaller. Another example is cesium, as you see. So those are the 2 critical conditions which bring about radioactivity. And these are the conditions which scientists base on to create what we call artificial radioactivity. So you just make an atom which is stable and turn it to be unstable, and in that case, it disintegrates. So with us understanding the aspect that is involved in radioactivity, can we define what is natural radioactivity? Boom, that is it. Natural radioactivity is if you have natural isotopes of elements undergoing disintegration. Like as we see carbon-11, carbon-14. They are natural, but they do disintegrate. So that is it with the natural radioactivity. Natural isotopes disintegrating. All the uranium also, the lithium also, all those are kind of under natural radioactivity. So artificial radioactivity. As we say, just get a stable atom, make it unstable, then it disintegrates. How to make it unstable? Find a way of increasing the number of neutrons. As simple as that. So, normally artificial radioactivity is considered as induced radioactivity. You make it happen, otherwise it wouldn't have happened. or sometimes it is called transmutation. You change one element to another. And this is the same knowledge which is applied in the nuclear power plants, in the making of the useful medical isotopes like maybe cobalt-60 and so on. The ones which are commonly used in treatment of cancer and other more diseases in hospitals, as we shall see in the uses of isotopes. So the question is, how exactly artificial radioactivity induced? Or how does it occur? So as we have seen about the stability, so artificial radioactivity occurs by bombarding stable atoms with either a neutron, which is the beta particle, or a helium particle, which is the alpha. And so as you bombard the two atoms, or the atom and the particle, then you create about instability, and the atom disintegrates. So two ways are followed in here. We call it nuclear fusion and nuclear fission. Remember we said do not miss the meaning of those two. So let's understand what they are. Let's understand what they are. Nuclear fusion. Fusion, breaking. You break. So in the nuclear fusion, as you see on the slide, just get your stable atom, for instance, uranium-235, bombard it with slow-moving neutron, it will break. It will, after some time, it will disintegrate to form stable krypton and barium alongside other neutrons, but these neutrons are faster moving and energy. Specifically, this is what happens in uranium nuclear power plants. You've always heard of the nuclear power plants in maybe Japan, you heard of nuclear power plants being said that they are being installed in Iran, and so on. So what happens, bombard a stable atom with a slow-moving neutron. And so with that, you are disrupting the structure and the composition of the atom, so it will disintegrate, as you see. So that is nuclear fusion. So with fusion, you bring atoms together, you fuse, you bring atoms together. This is a characteristic for bringing together lighter atoms to form heavier nucleus or to form heavier element. See the examples we're having. If you get phosphorus 31, this is the atomic mass, and you bombard it with a neutron, you'll get the isotope now, phosphorus 32. It is still phosphorus, but now this is an isotope. Remember, isotopes, they have different mass number due to different number of neutrons, but the proton is always the same. So this is the isotope of phosphorus being created. Look at another example. Get your hydrogen, bombard it with lithium. You'll get two helium atoms, or what we call two alpha particles. So in this case, you're combining two lighter atoms to form a bigger atom. That is called nuclear fusion. Nuclear fusion, you are disintegrating a big to form stable lighter atoms, as you see barium and krypton being formed. So that is artificial. This is artificial because it is controlled and it is made to happen. It is not happening naturally on its own. It is made to happen. And so this takes me to ask, Are there differences between artificial and natural radioactivity? Yes, they are. And what are they? Let's go through them on the slide. Natural, it is spontaneous. Artificial, or the induced, as we say, it is non-spontaneous. When we talk of spontaneous and non-spontaneous, we are looking at, can this thing happen without any external help? That is being spontaneous. With natural radioactivity, it occurs without any man's influence on it. Unstable atoms in the Earth crust, they disintegrate, releasing energy and other more radiations. That is natural. But for artificial, as we've seen, you combine, you bring atoms together for them to bombard and undergo radioactivity. Second, it is uncontrolled, as we said, for natural. Then for artificial, it is controlled. Controlled in a sense, you control the speed of the bombarding particles. You see that? How faster the incoming neutron or another atom is directed depending on the experimental setup. That is what we mean by being controlled. Lastly, usually the natural radioactivity involves heavier atoms disintegrating to form stable atoms or unstable lighter atoms. Whereas in artificial, you just get stable and induced. They can be heavy or they can be lighter because this is under your control. But for natural, they are normally heavy or lighter but very unstable. So the aspect in here is they are unstable. Aspect in here, they are stable. So those are the differences that we can look at. Now, looking at radioactivity, I'm posing a question to you students. Looking at radioactivity and chemical reaction, are they different? Do you see any similarities and differences in the two? Chemical reaction, the ordinary chemical reaction and reactivity. Yes, they are. And here are the differences. Simple understanding. As you can see, radioactivity involves the nucleus. It is the nucleus of the atom that is disintegrating. Whereas a chemical reaction, as you know, it is just simply the electrons outside the nucleus, which can be transferred or shared. Secondly, radioactivity releases excessively amount of energy. And that's why we are having the nuclear power plants producing electricity. And lastly, with the natural radioactivity, it is random, it is not influenced, but most of the ordinary reactions are influenced by the external environment. We looked at the factors which affect the rate of chemical reaction in the chemical kinetics, just the previous topic. So I guess you understand on that. So, uses of radioactive isotopes. The reality remains at this stage, we've all heard of X-rays or X-ray machines in hospitals. So when we're talking of X-rays, then of course we are meaning the radiation from radioactive isotopes. So uses, there are many, many uses. We may not all of them write them or quantify them, but there are many uses. We are going to put them in different groups. Applications in medicine, applications in research, and applications in industries, and so on. Looking at medicine, we all heard of cancer treatment using cobalt-60 and so on. This is, you can quickly go through that. I will leave you with even the exercise about that for you to understand what we mean. Then in industries, my emphasis will be on nuclear power plants to produce energy. This is the Beryllium power plant, you see. So it produces energy. And on that note, let me put much emphasis on the nuclear power plant with the focus on electricity production. electricity production. Yes, currently, many countries are shifting from hydroelectric power to nuclear power. Actually, as of 2019, in November, the World Economic Forum published an article about decarbonizing energy, and they found there are about 449 nuclear reactors in the whole world, which supply 11% of the world's energy. Among those, USA is leading with 96, and they generate 20% of the country's electricity, followed by France with around 58, which they produce 75% of the France's electricity. So now, someone may ask, why are we even having all this data? What is it for? I want to show you something in here, that nuclear power electricity is now what is the future source of energy. But what is very, very unwelcoming, in Africa, we only have 2 nuclear reactors which are found in South Africa. And yet, people are shifting from, this is now the setup of South Africa nuclear reactors. People are shifting from hydroelectric power to nuclear power because it is safe. According to the World Nuclear Association, it is safe, and the risks of accidents at the plants are very, very low. And as we've noticed, we are surrounded by many radioactive elements which we can put to use. So the emphasis of me giving you this knowledge is, I want to employ you, our future scientists. I want you to take note of this. You future scientists, to take courage and opt for nuclear science. This is where the future lies. This is where the future lies. Please, take note on the nuclear science and move and go much more about the knowledge and help to develop Africa. We need you scientists. So that is it for today. And as usual, I have to leave you with the exercise. The exercise is about how carbon-14 is used in carbon dating. Read more about it. It is a reading exercise. Thank you for being part of the lesson. And again, I implore you to take interest in nuclear science. It is the future, and you are the future. We want you to be part of the development of Africa. Bye.